Okay, so that's just getting the basic idea of a fundamental dimension across. There's also derived dimensions, and an easy place to get started with derived dimensions is, again, thinking about space, but thinking about space in more than one dimension. So I'm going to add another axis in a Cartesian coordinate system called y, and we're going to think of y also being fundamentally a length, some distance in space. That gives us the idea to think about another spatial property that we use a lot called an area. An area being some combination or some two-dimensional characterization in space. Now, you might be able to guess just from looking at this intuitively what the dimensions of area might be. They're a derived dimension based on there being two dimensions of length going into an area. Now, the dimensionality of area is length squared, but I didn't have to memorize that. I could derive it from any one of several equations. For example, the area of this rectangle is the length x, of variable x, multiplied by the length of variable y. Just like units, you can carry dimensions through calculations. That's going to be a big part of the homework I'll assign to this. So we can say if x is a length and y is a length, that shows us how area is a length squared because the individual lengths are multiplied by each other in this equation and we get a length squared. That also tells us that the equations like those for area are what's called dimensionally consistent. That means the left term of the equation has the same dimensionality as the right term of the equation. Dimensionally consistent equations are usually derived from fundamental theory, in this case, a fundamental geometric proof. And when you have this dimensional consistency of an equation, you usually have the property that the equation can be applied with any consistent application of a unit system. So it doesn't matter if x and y are in inches or centimeters. What you get on the other side of the equation is going to be a valid area with valid units, no matter what unit system you decide to use. So a lot of the more useful and generalizable equations that we use are dimensionally consistent because they're derived from fundamental theory, and you don't have to care about the number system that you're using to do the math correctly. The units on either side of the equation are automatically going to make sense relative to that equation. So we're going to talk a lot more about dimensionally consistent equations as we get further into this topic. So you don't have to take my word from it from a simple shape like a rectangle or a square. We can go through the same logic with a circle and convince ourselves that we still get a length squared. So the area for a circle, hopefully you remember, is pi r squared, pi times the radius of the circle squared. But we've got this tricky term pi. In order to figure out what the dimensionality of A is from this equation, we have to know what the dimensionality of pi is. So what are the dimensions of pi? Well, it might help to derive that because there is a definition for what pi is. And if you search back through your memories of geometry, hopefully you remember that pi is by definition the ratio of a circle's circumference to its diameter. So that is by definition, that's what that symbol means. It's identically identified as a circumference of a circle relative to its diameter. So that number is the same no matter how big the circle is. That's a constant. Hence we get that number 3.14, so on and so on. So we can derive the dimensionality of pi if we understand the dimensionality of the circumference of a circle and the diameter of a circle. Well, the diameter should be pretty straightforward. That's just a straight line across the circle through its center. That's a length, right? How about the circumference? What's the dimensionality of a circumference? That's a little trickier because it isn't a straight line anymore, but it is still a one-dimensional line. It's a different reference frame for that line, and then it's curved and not a straight line, but it's still a length. So if both the circumference and the diameter are lengths, those can divide out, and they result in what we call a dimensionless number. In notation, dimensionless numbers can be denoted with a 1 in the square brackets, indicating that it's a count. It's just a number. It doesn't have dimensions. So if pi is dimensionless, or a 1, That means it can be carried through the algebra with the radius squared. Well, the radius is half the diameter, so it's probably a length as well, right? It's a straight line from the center of the circle to the edge. That's a length. If you square that, again, we can convince ourselves that this equation can be used to derive that the area is a length squared as a derived dimension. Again, this is a dimensionally consistent equation. Again, any unit system is going to work in this equation. And so on, we can also think about a third dimension and think about a third derived dimensional characteristic of space that we frequently use called a volume. I'll use the variable capital V for this volume. We can use the same logic to derive that the volume of this rectangular prism, which is basically the product of the three lengths of its sides, is going to allow us to derive a dimensionality of length cubed for volume. So you multiply three lengths times each other. You can use the equation for a sphere to convince yourself this all works. Again, you're going to come up with length cubed as the fundamental dimension for volume here. So we can think of volume as being a dimension itself, but we can also break it down to the fundamental dimension of space called length in this length cubed. This is the idea of a dimensional analysis. And so far we've only been working with spatial dimensions, but this all works, and all of this algebra works with many more combinations of fundamental dimensions, especially those of time and mass, in terms of thinking about basic physics. And it's not just dimensional analysis. Sometimes it gets tied so closely to unit conversion that people think it's just about unit conversion, but it isn't. It's a much more powerful tool than that, as we'll work out as we move on. So next I will be talking about exactly what is a datum again, thinking about it philosophically, operationally, and diving deeper into this world of dimensional analysis.